Okay, so we are now on step 4 of Workshop 4. So up until this point, all we've really done is prepare our time series, get rid of any gaps, and we've also had a little look at how it's currently been sampled, so both the length and the time interval and what that means in terms of what kind of periodicities we can observe. Okay, so now we're going to actually get to the meat of this workshop, which is really to try changing both our sample length and the sampling rate. And step 4, we look at step 4, it says explore the effect of sample length on the mean of our time series. Okay, so we need to write a script to find and plot the cumulative average, plot the results, and try and find out how long we need to sample before the mean stabilizes. So what does all that mean? Well, if we just refer to the PowerPoint slides from the lecture, you might recall having a look at this time series here, which is a time series of, well, it's actually of current speed, but you can see how we're looking at it on a scale of well, 1,000 seconds, so minutes worth of current metadata, and you can see that there is a very high frequency fluctuation here, which will be the turbulent components of the velocities. But when we are, measuring tidal currents, we don't necessarily need to know what all these fluctuations are. What we might want to know is, say, what is the average current speed, in the surface water, on the peak flood or something like that. And in order to do that, you need to determine how long a time series you need to sample for in order to get a mean which makes sense. So you can see with this particular time series, if we take the mean over like 10 seconds of data recorded in this time interval here, we'll get a very different result than if we measured the mean over this 10 seconds taken from 600 on the time axis here. Okay, so the mean is variable within our time series. So we've got a fluctuating mean to some extent, but what we want to know is what is the mean on the time scale of interest. So if we're thinking about a flood tide, then you might be thinking, well, maybe an hour's worth of data makes a bit more sense. So if we ignored the tidal component, tidal oscillating component, and weren't too worried about like net or residual flow velocities, then and we just want to know what's happening at that particular time during the tidal cycle rather than looking at the high frequency variations, then we'd want to see what happens to the mean and how it changes depending on how long we average for. So this plot underneath shows us the cumulative mean. So in other words, if we start from 0 and we start averaging over the velocities that we've got for every time step, so if we take up to 200 seconds and we take the average, then it would give us this value here. If we average over 400 seconds, we would get this value here. And you can see how for this particular time series, the average starts to even out and doesn't really change much after about 300 seconds, say. Okay, you're still getting some fluctuations, but you're not getting the same degree of change that you do in the first 200 seconds, where you can see that if you only sampled for, say, 50 seconds or 100 seconds, then you would get quite a different result for your average than if you were to sample for 600 seconds. Okay, so we need to check for convergence of mean in order to determine how long you need to sample your time series for. So if we just get rid of that again and go back to where we are here. So we're exploring the effect of sample length on the mean of our time series. So we need to write a script to find and plot the cumulative average, basically to do what was shown in that last slide. Okay, so we go back to our MATLAB command window. You notice that in my workspace here, I've still got the time axis that we're working with, which is TD1, and you'll remember that we had interpolated our original tidal height data, and we have put that in a new variable here with no gaps in it, and it's called H1 new. Okay. So what are we doing now? So first of all, I guess we need to write a new script, a new function, by passing it this time series, the H1 new and TD1, and finding the cumulative average, and then plotting that up. Okay, and then we can see the point at what time it starts to say it's stabilized, the mean starts to stabilize. So if we start a new script called cumav, okay, .m, cumulative average function, so does not exist. Yes, I want to create it. Okay, so this is a function, and we want it to output we want it to output a y value, which is a cumulative average, so cav, say, and we have called this function cumav, and we're going to pass it a time and a y variable, which will be our interpolated time series at tidal height. And then just a little descriptive bit of information. So this function finds the cumulative average of regularly spaced time series y of t, which is what we've input here. Okay, so we can make use of one of MATLAB's inbuilt functions here. If we go back to the command window for a moment, if I type in that particular command is called cumsum, so I type that in, then you can see this is the syntax here, and look, just reading the description, it says B equals cumsum A returns the cumulative sum of A. Okay, so this is what we are putting in. This would be our tidal height data, starting at the beginning of the first array dimension in A whose size does not equal 1. Okay, so we don't need to worry about that part, the second part, too much, because A is a vector. A is a vector, so it returns a vector containing the cumulative sum of all the elements in A. So that's quite easy to employ. So what's happened to my editor window? So we want to output a y value, which is the cumulative sum, so csum, and then we're going to use MATLAB's inbuilt function cumsum of our input y variable, like so. And then to find the average of that, well, each summation, which is in the variable y csum, you just divide that by the length of the time series at that point, so at the index point, basically. So if we want to find the cumulative average, y cav, then that will be equal to y csum, and that will be divided by the indices of y, which go from 1 to the whole length of the time series, to the length of y, or it could be y of c sum, doesn't make any difference because they're the same. Okay, so that will give us our cumulative sum and our cumulative average. So we should be able to plot those out quite easily, generate a new figure. And let's plot out the original time series and then the cumulative sum and then the cumulative average. So we'll have 3 subplots here. So subplot 311, and we'll plot the original time series here, which will be t comma y. Make sure we label it so we know what we're looking at. This one's the time series. And our X label is time in days. And our Y label is tidal height, water elevation in meters. And then we'll do the same thing. Just copy the whole thing below it and generate a second subplot. But this time we're going to plot the cumulative sum, so YC sum, and this is now cumulative sum, and we can generate a final one, subplot Y3 313, and this is to plot the average, cumulative average, C av. So we'll change the time series label here to cumulative average. I suppose we should probably change the Y label as well. Well, it's still water elevation, it's just averaged. Okay, so we'll leave that. So that's our function written. Save it, minimize that. And so we want to call that function and output our, do we need to output our cumulative data? Yes, we might as well save it. So HCAV is equal to our cumulative average function, and we're going to pass it our time series, which has been interpolated, so TD1, so our truncated time series to 200 days, and our tidal height information, which has been had all the gaps filled in. Okay, let's see if that works. Okay, good. So let's just have a closer look at what we've got here. Okay, so you can see in the top plot we've got our original time series, with not the original, but our interpolated time series, which we truncated at 200 days. So no gaps in that one. This is the cumulative sum. In other words, you're just adding up consecutive points all along here. That's fine. It's increasing, which is what you'd expect. Okay, cumulative average. Okay, so you can see how you get quite a bit of fluctuation initially in the first few hours and days. Quite a lot actually within the first few hours or days. But then after about 20 days or so, you can see that you get a reasonable average. So what you might expect for water elevation within a given week is not necessarily going to represent what you might consider to be the water level, water elevation on an annual basis. So an annual mean needs to be represented by sampling for about 20 days. Otherwise, it looks like your mean has not had a chance to stabilize. Okay, so if you're looking for the mean of this particular time series of water elevation, then less than 10 days is really not long enough to give you a value that represents the annual mean. Okay, so that just gives you an indication of how the length of your time series makes a difference to the average that you calculate. Okay, it's also clear that although it doesn't completely it doesn't completely flatten out. So there's obviously some other longer term fluctuations here that is not being resolved on an annual basis, and we might need to sample over even longer if you were to want to find out what's happening with that average here, or what that fluctuation is a response to. Okay, I mean, sea level rise would only be detectable perhaps on a basis of a number of years, but over a year we can't really see that, and certainly within 10 days or so you're not getting anything that's representative of the annual mean. Okay,